Well, hello everyone. I'm back with the part two to this idea of the total line hack. And I thought I'd seg you this time into systems of equations and to show you its real value is really in that chapter. And so I am going to first though review real quickly the hack because if you're just tuning in, this is going to throw you for a loop. And so let's just do it real quick. Now remember I said to run the hack, you needed to be sure that the equation was in standard form. And in other words, this form right here, alphabetical order with the variables on the left side, like so, 3x plus 2y, and then the constant, the lone number, on the other side all by its lonesome. And so once you have it in this standard form, the idea was to go ahead and form up this half-formed A in your mind or with an actual pencil. And that created two fractions that gave you the slope and the y-intercept. There was one slight trick though. Well, you had to remember that the reason why we drew this half-formed A is that it told us what was the top of the fraction and what was the bottom. What was the top of the fraction and what was the bottom. What's in here is always the bottom. And then the slight nuance was that when you formed your fraction here for the slope, you get 3 over 2, but you always have to put a negative sign in front of those numbers. And so you get actually a slope of negative 3 halves. For the y-intercept, you simply put 12 over 2 and you get 6. And so the y-intercept is 0, 6. That's where this line will pierce the y-axis. So that was the slope and the y-intercept simply read off of an equation without doing any algebra, without the normal route which is taught, which is namely to manipulate the equation into slope-intercept form and then read off its m and its b. Now that certainly works good, but if you can simply do this like so and not have to do any math, not have to do any switching of sides, adding and subtracting, how much better is that? How much better is it than that you eliminate the chance of errors? So that's one argument for the hack, but the real argument is that when you're in systems of equations, you want to be able to look at a system and make a decision if it has a solution or not. Now, I talked about systems of equations, and I said when you first get an introduction to this, it's best to look at the major ideas and not worry the computations at first. So let's look at those major ideas again. Let's imagine we're standing over this xy axis. It's on the floor, and we're going to drop sticks, long, thin sticks or lines at random onto this xy axis. And let's ask ourselves, what are the situations that can develop? The first one that's going to happen a heck of a lot is when we drop those sticks, is that they're going to fall on top of each other like that. And they're going to intersect in one point. And so in terms of math, we say the system has a solution, it's consistent, and the game is to use the techniques that are taught in the chapter to find that point. Now, I'm not interested in those computations. I'm interested in the overarching idea, and that is that this is going to happen a heck of a lot when we form up a system, and that the key thought here is that the lines have different slopes. And that's true for, I imagine you do this thought experiment. Sit back on your sofa and imagine if you could find two lines with two different slopes and not have them intersect. You really can't. If two lines have different slopes, they're going to intersect somewhere. And so that's the main idea here. Now another situation that could develop when we drop those two sticks is that perchance they may drop right next to each other. They may be parallel to each other, in which case they have no points in common, in which case we say the system is inconsistent. Now, in terms of our overarching ideas, notice the slopes, the slants with the horizon here, are the same for both lines, but that their y-intercepts, where they intersect their y-axis, is different. So we have two situations. When the slopes are different, we have a solution. When the slopes are the same, but the y-intercepts are different, we have no solutions. There's one more situation that can happen when you drop lines. And that would be very rare indeed, and that is if the two sticks, fell right on top of each other, in which case they have every point in common, and they would have infinitely many solutions, so to speak. Well, keep in mind, where my hand is sitting right now, the point under there is not a solution. So there's still some constraints. Not every point is a solution, but every point on this line or the other line would be a solution to the system. And there are infinitely many of such points. But in terms of the overarching idea, the slopes of these two lines are the same and their y-intercept is the same. Those are the ideas you want to keep uppermost in your mind. Now, what I've done here is I went searching the other night online for free online textbooks, and I actually found a online college algebra textbook. And chapter 5 is its chapter dealing with systems of equations. And I was checking out the problem set here, and I selected some problems to work and use our hack and talk about the overarching ideas on. So let me drag those on in here. Here's the 3 problems I want to look at. And let's get after it. I want to bring in the drawing program too. And so, what do we have here? We're going to look at this first system here. And so, here are 2 lines, and we want to know if they have any solutions, if it's consistent. And so if the slopes are different, then because the slopes are different, they have to intersect in one point. So I want to use my hack right off the bat to just to see, before I even do any computations, to see if the lines' slopes are different. And so, in my mind's eye I would do this, but since you're learning, let's go ahead and form up the half-formed A. For the slope of this first line is going to be, you take those 2 numbers, 2 over negative 3, and you put a minus sign in front of them, 2 over negative 3, put a minus sign in front of them, and that's the slope. And so what do you get there? That's actually a double negative. It's actually 2/3. So the slope of that first line is 2/3. How about the slope of this line here? Go ahead and form this up, and we put 5 over 4 with a negative sign in front of it. And so there's the slope of the second line. Now, these slopes are different, and because they're different, I know this system is going to have a single solution. It's going to intersect in one point. And I'd be free and clear to go ahead and do the computations on it, since I know it has a solution. It only takes me a second to use the hack and to check the slopes of the line. Now what about the second equation, second system of equations? Let's go ahead and form up the half-formed A. The slope of this top line is going to be 4 over negative 2 with a negative sign in front of it. And so the slope is 4 over 2, or 2. The slope of this second line is going to be 6 over negative 3 with a negative sign in front of it, or 6/3, or 2. So these lines have the same slope. And now we're concerned to see the y-intercept. Are they the same y-intercepts, in which case they'd be the same line, or do they have different y-intercepts, in which case they're parallel lines? And so the y-intercept of this first line is 5 over negative 2, which I'll write the minus sign up top, so it's 0 comma negative 5/2. The y-intercept of this second line is negative 10 over negative 3, or simply 10/3. And so these 2 lines have the same slope, yes, but they have a different y-intercept, so they are parallel, and there are no solutions to this system here. Now, notice I didn't use any of the computations available in our chapter. I didn't use elimination, I didn't use substitution, I didn't use Cramer's law. I simply looked at the slope and the y-intercept and realized that I had parallel lines and there was no solution. This third situation, let's try it. Again, we're going to form this up. The slope of the first line looks to me, I'm going to quick step this, it looks to me to be 2/3. And the slope of the second line looks to me to be 2/3 also. Actually, it's 4/6, but that reduces to 2/3. So again, we have a situation where the lines have the same slope. And now we're going to look at the y-intercept to see if they're the same line or if they're parallel lines. Over here I have negative 1 over negative 3, which is going to be just positive 1/3. And on this other one I have 2 over 6, which is also 1/3. So these are the same lines. They may not look identical. On reflection, I see if I multiply this top line here, both sides by -2, I get this second line. So in fact, they are identical lines, and because of that, they're going to have every point in common that's on this line is going to be on this line. They're going to have infinitely many solutions. How would we show that? Well, we would say something like this. The set of solutions is going to be all ordered pairs such that those ordered pairs satisfy either this line or that line. You pick one. I'll pick the top one. Such that those ordered pairs satisfy that equation. And that would be a way of writing that solution. So there you go. I got an answer for the second one and the third one without even using any of the techniques of elimination or substitution. I know I need to use those techniques here because the slopes are different, and so the lines are going to intersect in one point, and I would go ahead and use my techniques. But as you can see, this idea hacking these systems by first looking at their slopes and their y-intercepts is very powerful and keep you out of trouble. I guarantee if I was to put this one on a midterm, I guarantee that a lot of people would find solutions for this. They would run their techniques and they would come up with something. They'd make an error and they'd come up with something. They'd never even realize that the lines are parallel and therefore there is no solutions. So I think you can leverage the idea to good power. I hope this helps. You may have to watch it again. There's a lot of ideas here, but I think they're worthwhile. Be talking to you again soon.